Yes, in the last lecture, I was showing that there is a, so what we had derived was that u dy, which is the flux from this side of this control volume minus u naught times h. Okay, so let us just look at this in the dimensional variables for now. I think there was some confusion about this, how minus h by 2 and plus h by 2 had taken half and things like that. So dimensional quantities, if you look at, then you can directly very easily integrate your mass equation and obtain this. Okay, that u dy minus u naught h is not equal to 0 actually, and it will be equal to, so what was the quantity that we derived? What was the dimensionless quantity that we had derived? Hmm? We had derived dimensionless. Can you tell me that? I can convert it into dimensional. What was it? So if this length is, let us say, L, or let's say we are looking at some downstream distance x also, then you will get something like, so this you get by integrating del u by del x, so minus del v by del y when you integrate, so you will get v for y tends to infinity comma x minus v y tends to minus infinity comma x integration of this quantity dx. Okay, this is what you will get. And if the flow is symmetric, then we can write this as, so v of minus y is equal to minus of v of y. So we can write minus 2 v y tends to infinity dx. Okay. So this is what you will get if you do the integration. Basically, I'm just integrating del u by del x plus del v by del y equals 0 over the control volume. Okay. I hope there are no doubts in this procedure. Integrating this over CV, and this is your CV. Now you can do the same thing for your momentum equation. So what we have derived is u del u by del x plus v del u by del y equals, so we have already reasoned that pressure term is not present, and in the dimensional coordinates, and variables, I will get a kinematic viscosity here and a del 2 u by del y square. I'm changing things to dimensional coordinates because I realize that either if I have to follow non-dimensional equations, then I need to do that whole procedure in front of you. I cannot do it on the fly because I might make some mistakes and it is not easier to understand also. And so let's stick with dimensional equations, okay, for this problem so that you guys understand what is going on. And you should realize that we have argued, so we have derived this equation in the dimensionless form. Okay, if you plug in the scales back, you will get this equation. Okay, whatever scales are being used, if you plug them back, for example, if you have an equation in u star del u star by del x star plus v star del u star by del y star equals del 2 u star over del y star square, and if you plug in that x star is basically x over L, y star is basically y over h, and u star is basically your u over u naught, and v star is, I should not use these, v star is basically v over the scale of y direction velocity, which will be u naught h over L. So if you just plug these back in, inside this equation, you will get this. Okay, so I am just trying to follow the procedure here. Now some of you may be asking, okay, how will you get this new, because you will get a Reynolds number and things like that, right? Because H and L, remember, we are doing it in the limit of this. Okay, we are doing when this is upheld, and REL, which is U naught L over nu, is much greater than. So these two conditions are required for all this analysis, and these are basically the combination of these are the boundary layer theory approximations. Okay, so plug in these dimensionless quantities and you will get the dimensional form. Okay, so let's work with dimensional form, and let us, what we will do is we will integrate this equation over the control volume. Okay, we will integrate this equation over the control volume. So I will write, okay, I will write this, and remember that we are taking a limit of a control volume that is extending to y towards y tends to infinity in both the plus and minus directions. Okay, so essentially the limits of the control volume in x look like, let's say, this, and in y they look something like this. Okay, you can write it as some minus h, capital H to plus h, and evaluate it in the limit of h tends to infinity, if that is easier for you to think. So you can write it like this, and evaluate this in limit h tends to infinity. Okay, now if you look at this term, this is a complete derivative, right? This is del by del x of u square by 2. Okay, this is del by del x of u square by 2. So you do the dx dy integration, you will get basically u square by 2 at x minus u square by 2 at x equal to 0 dy from minus h to h. Okay, now this term is not really a complete derivative. Okay, v del u by del y is not a complete derivative. So how do we treat this? How do you think we can treat this? Hmm? How can we treat this equation? Hmm? How can we treat this term v del u by del y? Hmm? How do you use continuity? You have del u by del x and del v by del y there. Continuity has these. So how do we treat this term? Hmm? Anyone? Anyone has any suggestion to make here? How do we treat these terms? And so I'll give you a hint, you are in the right zone. We have to use continuity somehow to to make them complete derivatives, or to see if we can make them as complete derivatives. But so you will have to see how to substitute del u by del x as minus del v by del y. Okay, we were hasty in doing this. So first of all, this term I can write as del by del y of u v minus u del v over del y. Okay, this term v del u by del y I can write like this, and now here I can use continuity, or instead of substituting del u by del x here, I can make this as a derivative by doing this. So, minus u del v by del y is plus u del u by del x. Okay. And now all the terms are complete derivatives. So, we have minus h to h 0 to x del by del y of u v, and then here you will have plus del by del x of u square by 2 dx dy. Okay. So, we will get another term of this value. So, when you add these two, you will get minus h to h u square at some x minus u square at x equal to 0 integrating dy, and then a plus minus h to h 0 to x del by del y of u v dx dy. And then on the right hand side you have something very straightforward. You have minus h to h 0 to x del to u over del y square dx dy. So, this term if you look at, you can't do anything about this. So, we are evaluating all this in the limit h capital H tend to infinity. So, you really can't do anything about this one, you really have to just carry on this integration if you knew about it, but this you know u square at x equal to 0 is u naught between minus h by 2 to plus h by 2 and 0 everywhere else. So, this integration is simply going to give you minus u naught square h. Okay, this integration is going to give you minus u naught square h. What about this guy? So, I can change the order of integration assuming everything is smooth and nice. So, I can change this order of integration and I will get u v y tends to h tends to infinity minus u v h tends to minus infinity integration dx from 0 to x. Here I will get nu times 0 to x del u by del y from h minus del u by del y minus h dx. And so, what do we get from this? So, what can you say about u v in the limit h tends to infinity? What can you say about this u v in the limit h tends to infinity? Now, we have said that you cannot just ignore the integration of v in x, you cannot just ignore this. V might be very small, but if you are integrating over a large enough distance, that is not going to cut it. But you know that u is going to be 0 for h tends to infinity. That is how we have made this. That is how we are saying that far away from the jet, why would there be any x direction velocity? There is no entrainment that has started to happen. So, we say that u for y tends to infinity or h tends to infinity plus minus infinity is 0. So, these terms are 0. Similarly, we are saying that u is approaching 0 smoothly. So, even del u by del y, which is basically the shear stress for plus minus infinity is 0. So, these terms are also 0, and this tells you that this constraint always holds. Okay. So, in a jet flow, your mass flux or volume flux, if you just ignore the density, is not constant in x, because you have a you have a continuous entrainment of the fluid from the sides that is moving along with the jet. But what is constant along the x direction is this guy at all x locations u square dy, which is not the mass flux, but if I multiply this momentum, then what is this? If I multiply this with density, what is this? Momentum flux, right? This is momentum flux. So, technically the mass flux is not constant, the momentum flux is constant in x. So you can treat these as our assumptions, or you can say that they are at the leading order, these things are 0 because u is approaching 0 smoothly. Okay. So if any quantity is approaching 0 smoothly, it is going to get, it is going to be an asymptote to 0 for y tends to plus minus infinity or h tends to plus minus infinity. You can call these assumptions as well. So rho u square dy is rho u naught square h. So you have momentum flux which is constant in x. Now an important point I want to make here is that I know I have gone in the opposite direction compared to your other classes in fluid mechanics, okay, where you assume that control volume implementation is there, but you can derive the differential equations. But since in our course we have already shown that differential equations are fundamental, and then you get these control volume equations if you want to do the derivation from first principles of continuum mechanics. So that's why I followed that procedure, that I assumed all differential equations to be without any assumptions, of course after boundary layer approximation, and then I integrate them over a volume. Okay. Constant in x. So with this we will try to solve our jet equation. Okay. And as it happens, this is a particular case where a analytical similarity solution is actually possible. Okay. An analytical similarity solution is possible. And so what we will do is we have our governing equation, the momentum equation, and then we have the continuity equation as well. Okay, we will start with our similarity guess, which is something that you guys will be provided in your exams. So we will start with our similarity guess, and instead of making a guess for velocity directly, so I could have followed this procedure in boundary layer also. So but I didn't want to introduce it there. I'd like to introduce it here. And the idea is we start with this similarity guess as a B here. Okay. So instead of approximating velocity, I am writing the similarity guess, or instead of writing the guess for velocity, I am writing it for the stream function. Okay. So this is your stream function. And the idea here is that if I work with stream function, then my continuity is automatically satisfied. Okay. By the definition of stream function, we will have u as del psi over del y and v as minus del psi over del x. So I won't have to worry about continuity equation if I work with stream function from the beginning. Okay. So this is what I use as a similarity guess. Now where does this come from? It needs a lot of years of practice of applying similarity solutions to different equations, or if you take some advanced courses in PDEs, then you can learn how to use this trick. How did we come up with this kind of a similarity guess? Okay. But accepting that this is the guess, now our job would be to find basically P, Q and A, B. Okay. And as you will see in all our boundary layer examples, we have had one arbitrary constant that always remains. So you can immediately sort of predict that we'll have some constraint in A B, but that's pretty much it. We'll have just single equation that will determine A and B. So you'll have to choose one and then you'll have to find the other. Okay, but we'll get there. So we have this as our equation. So now it's all about algebra. So you put q as del psi by del x, del psi by del y, which is going to be a x to the power p f prime by b x to the power q. V is del psi by del x minus sign. So this becomes ap x to the power p minus 1 f minus a x to the power p f prime y by b x to the power q. So we'll have, let's say, eta and then a with a minus q over x, right? So p minus 1. So it'll be a p x to the power p minus 1 f minus a q x to the power p minus 1 f prime eta. Okay, this is what we will have. Yeah, this is what. Huh? There'll be a minus sign. You're right. Okay, so this is our v. Then we have del u by del x. So let's write u as a by b x to the power p minus q times f prime. So what is del by del x? Del u by del x, a by b and then a minus x p minus q f double prime. So divided by b and then we have a q x to the power. So y by x to the power q plus 1. So one of them becomes eta and then we are left with an x in the division. So we'll have this. So we have a by b p minus q f prime minus q f double prime eta times x to the power p minus q minus 1. Del u by del y is luckily easier. So you have a by b x to the power p minus q f double prime by b. So b square divided by x to the power q. So p minus 2q. And what is del 2u by del y square? A by b cube x to the power p minus 3q f triple prime. So let us substitute all of this in our equation. Okay, so we'll get, so let's write one by one. A u del u by del x is a by b x to the power p minus q f prime, and then this big term a by b whole square p minus q f prime minus q f double prime eta x to the power p minus q minus 1. Okay, so it looks like a lot of algebra for a solution that will, I mean, at least to me, I find that solution to be worth it, because you have a closed form solution of something which is governed by nonlinear PDEs. So again, this is one of those nice examples where you can do that. So this is u del u by del x, and then you have a v del u by del y. So we have a q f prime eta minus p f times x to the power p minus 1. This is v, and then we have a del u by del y. So a square over b square, this times x to the power p minus 2q f double prime. This is v del u by del y equals nu del to u by del y square, which is easier. Okay, so for a minute, let's just combine all of these x powers. So this is p minus q, this is p minus q minus 1. So we will have 2p minus 2q minus 1, and here as well we will have 2p minus 2q minus 1 f double prime. So what can we cancel out from here? What all things can we cancel out? So let's try to make the coefficient of f triple prime as 1. So let's divide everything by this quantity. So we have f triple prime. What do we have here? So multiply this thing with b cube by nu a x to the power p minus 3q. That's what we are doing. So what do we get for the first term? A times b. So this equals a times b over nu, and then we have a x 2p minus 2q minus 1 minus p minus 3q. What do we get? So what do we get? 2p minus 2q minus p plus 3q. So x to the power p plus q minus 1 f prime p minus q f prime minus q f double prime eta plus again ab over nu x to the power, we have the same exponents p plus q minus 1 f double prime f prime eta minus pf finally. Anything cancelling out? Anything cancelling out? So this is same in both a by b, ab by nu x to the power p plus q minus 1. So if you look at this second term, this is q f prime f double prime eta, and here the first term is q f prime f double prime eta. So these guys will cancel out, and we will be left with f triple prime equals ab by nu x to the power p plus q minus 1 and p minus q f prime square minus p f f double prime. Okay. This is what we are left with after using this similarity guess, substituting it in our governing equation. So for our similarity guess to be valid, what is the condition that we use? For the similarity guess to be valid, for there to be a similarity solution, what do we say? So this should be an ODE in eta. So this guy should not be a function of x separately, everything should be a function of x and y through eta. So p plus q should be 1. So p plus q should be equal to 1, but we have p and q. So where does the other relation between p and q come from? And that comes from actually here, where we did the momentum flux, where we showed that momentum flux is constant. So if you consider this u square dy, u is that guy, this a by b x to the power p minus q f prime. So this is a by b whole square x to the power 2 times p minus q f prime square dy. Okay. Now dy you can change to d eta using that. So dy is what? B x to the power q d eta. So that means u square dy equals a by b whole square x to the power 2 times p minus q b x to the power q, and then I can write, so when y is tending to plus minus infinity, eta is also going to go plus minus infinity. So for eta I use the same limits, and f prime square d eta, this should be a constant. right? Rho u naught square h, that's not varying in x or y. So, this should be a constant. When can this quantity be constant? So, eta you are eliminating out by integrating it. Okay, you are integrating from minus infinity to infinity in eta. So, that is gone. What is the other thing remaining? X. This should not be a function in x. Okay, this momentum flux should not be a function in x, because we have shown this is constant. So, this is a constant only when 2p equals q. This thing is constant. Okay, 2p minus q equals basically 0. So, 2p equals q, only then you have this as constant, and then we have p plus q equals 1. So, that means what? P is what? And q is 2 by 3. So, we have found the conditions under which we have a self similar solution to our equation, and notice what we had to use. We substituted this as similarity guess. This is the equation that we obtained, and then we have this. Okay. Now, where was the jet specific part here? Where was the jet specific condition that we applied? This equation, as we know, is applicable to 0 pressure gradient boundary layer as well. So, P plus Q equals 1 is not really a jet specific condition that you have obtained, it is this condition that the momentum flux is constant 2p equals q, because if you go back to your flat plate boundary layer, the Blasius equation derivation, you will see if you convert the similarity guess for u and v, if you convert it into psi, you will get p as half and you will have q as half. So, p plus q equals 1 there as well, p plus q equals 1 holds there as well. This condition is not specific to jets. The jet specific part is this thing where we have 2p equals q, because momentum flux has to be constant. Okay, the reason I am saying this is because there may be other problems in exams or somewhere where the same equation is valid. Okay, and I am saying now, and you can quote me from this lecture, if you show all of this, okay, if you show all of this and you reach this equation, okay, or if you just say that as derived in class, we have shown this to be true, in both cases I will give you full credit. Okay, because I really do not want you to go through all of this algebra. I mean, you can, and I think there are benefits of going through this algebra, but since for this particular equation without pressure gradient term here, if you start with this similarity guess, you are always going to get p plus q equals 1 should hold, and there is no point really, I think. Okay. I mean, as long as it is about an exam, there is really no point going through all of this algebra and then leaving out other questions and saying that this took me time. Okay. So, I am giving an opportunity to save time. Maybe in your sheets you can write this derivation down, and but you will have to write the final forms. Okay. So, you will have to write this in exam, this if I am giving the same similarity guess. Watch out, if I give a different similarity guess, then please do not write the same thing, and you can write this. Okay. These three things you will have to write if I am not giving you explicitly a different similarity guess. So, this is not the second condition. In the flat boundary layer case, the second condition came from where did we get that the delta is square root of x? How did we get that delta is square root of x? So, if you go through that, okay, your u infinity was constant, basically what you will get is you began with this guess assuming P and Q both are equal. You began with this guess assuming both P and Q are equal. Okay. Basically, in terms of delta, your psi was simply u naught delta of x times an f eta, and eta was simply y by delta x. So, you started with the assumption that both of these exponents p and q are anyways equal, because you had the same function delta of x. You had the same function here. Okay. Here you don't have the same function. Okay. And as you can see, if you write this as some delta, let's say, okay, if you write this b x to the power q as some delta, then q is 2 by 3. 2 by 3 is larger than half. Okay. 2 by 3 is larger than half. So, the increase in this jet thickness is actually faster than the boundary layer. Okay. And this goes back to our discussion earlier when we were discussing that how do we estimate this length scale delta when we were doing the non dimensionalization, how do we estimate this length scale delta. And what I had said that in case of a boundary layer, this delta is a diffusion thickness, but in case of your jets, this delta is not quite the diffusion thickness, it is something which is varying with x as 2 by 3, not half. Okay. So, intuitively you can think about it like this: you have, let us say, a boundary layer, and this x, the delta, is growing as a diffusion thickness as you move downstream. If it is growing faster than the diffusion, then there is some other physical mechanism which is helping this delta grow. What is that physical mechanism here that is helping the delta grow? It is the entrainment of the mass flux, which we showed that there is some v velocity at minus plus minus infinity, which is getting dragged along with the jet. In your Faulkner scan boundary layers, you will find for different cases the delta's variation on x is different. For example, for that stagnation point flow, you will see delta is constant. Okay. So, the intuitive way of thinking about it is that you are impinging the flow, and that impingement is trying to suppress the growth of delta. Okay. So, if you have a flow which is, let us say, which is capturing the effect of, let us say, flow going upwards. So, when will a flow go upwards? What will happen to del u by del x if the flow is going, let us say, upwards? If your v has to be positive, v is 0 at the wall, v has to be positive above the wall. So, del v by del y has to be positive. So, del u by del x has to be negative. So, if you have a free stream velocity which is decreasing in x, a free stream velocity u infinity which is decreasing in x, then you can expect that your boundary layer growth will be faster than x to the power half. Okay. And when do we have du infinity dx less than 0? What was the pressure gradient case when you have du infinity dx less than 0? If du infinity dx is less than 0, then what about dp dx? dp dx is greater than 0, it is an adverse pressure gradient, and you can intuitively think about it, right, that the flow is slowing down. When is the flow is going to slow down? When the pressure gradient is adverse. Okay. Here the intuition about Bernoulli's equation is perfectly valid, because here we are deducing things from the inviscid zone. Okay. So, there are more profound things that you can think about rather than just algebra, that what do these exponents q 2 by 3, p 1 by 3, what do they actually mean? What they mean is that the growth of this delta of x is faster than half, x to the power half, because there are other physical mechanisms which are either promoting here in this case, because 2 by 3 is greater than half. If the exponent we had arrived at was less than half, then there are some other mechanisms which are demoting the growth of this boundary layer or whatever layer you are looking at. Okay. So, this kind of physical thinking from mathematical relations that we have arrived at is very important in fluid mechanics. Okay. It is actually completely reverse of what you have maybe been trained to do and things like that, that you apply your physical intuition and put it into maths. No, do the maths first, then build your physical intuition. Okay. So, we have a condition we have two conditions. We have found P and Q. So now we are in the state of being able to solve, hopefully, this equation. So what is the equation going to be when I substitute the values of P and Q? I know P plus Q minus 1 is going to be 0. So F triple prime is AB over nu P minus Q. What is P minus Q? Minus 1 by 3 F prime square minus P 1 by 3 F double prime. So the equation that we are left with is F triple prime plus AB by nu or AB by 3 nu F prime square plus FF double prime equals 0. We are not fully done yet because we still have to look at if boundary conditions collapse. From 4 boundary conditions, you are left with 3 boundary conditions, only then you have a closed system. Okay. So let us look at the boundary conditions. Okay. So what was the boundary, what are the boundary conditions for y tends to, let's say, plus minus infinity? For y tends to infinity, you have u goes to 0. Remember our derivation of the constant mass momentum flux. We are saying that u direction velocity is 0 for y tends to infinity. What was u direction velocity from this psi? What was u direction velocity? Just look at your notes. So you will get a by b x to the power p minus q f prime. So this means f prime for eta tends to infinity is 0. What is the other boundary condition that we can make? Hmm? Can we say something about f primes and all those are fine? Can we say something about f? Hmm? So let us look at v. Okay, v had what? Something and then an eta f prime minus f, right? Hmm? What can you say about v at eta equals 0? When y is 0, what can you say about v? Why? Symmetric. The flow has to be symmetric. So y direction velocity is going to be 0 at eta equals 0. So that means f of eta equals 0 is 0. And since you have used symmetry, the other condition of symmetry is del u by del y has to be 0 at y equal to 0 because this is symmetric. Okay. So from here you will get that, what will you get? F prime eta equals 0 is 0. You can do that, and that's exactly what, hold on, del u by del y was what? F double prime, right? You can do that, del u by del y going to 0 at y tends to infinity, and you'll be able to show that if you use either of these conditions you'll get the same solution. Okay, you can do that. So instead of these two conditions at eta equals 0, you can use 2 at eta tends to infinity also. Okay, and as in a moment you will see, you can do that, and let's see if it helps us in solving the equation. So how do we start solving this equation? How do we start solving this equation? Is there a complete derivative that we can form anywhere? Hmm? So we have f triple prime plus AB by 3 nu f double prime square plus ff double prime. This f prime square plus ff double prime, what is this a complete derivative of? Ff prime, right? So, this is basically f triple prime plus AB by 3 nu ff primes prime equals 0. So, we can at least do one integration in eta, and f double prime plus AB by 3 nu times ff prime equals a constant, let us say C1. Okay. What can you say about ff prime and f double prime? Here we can still form full derivatives. Ff prime is what? F square by 2 prime, right? Ff prime is okay. So, we have f double prime plus, so let us do this as 6 equals C1, and then f prime plus AB by 6 nu f square is C1 eta plus C2. How do we proceed from here? Can we solve this? Can we solve this? Can we solve this? So, one thing is clear, that for this equation to be valid for eta tends to infinity, this equation has to be valid for eta tends to infinity, your C1 will have to be 0, because if your C1 is not 0, all of these things are functions of f. You cannot just obtain that you have a linear dependence on eta, because this equation has to be valid for eta tends to infinity. So, you can reason out that C1 has to be 0, and you have a constant, and then you have an f prime equals some constant minus another constant f square, and this is an equation that you can integrate. Okay, this is an integration that you can do, and so we'll try to do that in the next lecture.